Hi there, my name is Miss Townsend and I love math. Welcome to Math with Townsend. This video is for grade 11 students working on the year-end summative for functions and relations. It's question number 10. It says, a toy tractor wheel has a radius of 1.5 centimeters and rotates clockwise. A stone is embedded in the rightmost part of the wheel. And we're going to have to sketch a sine graph for the height of the stone above the ground, write an equation for the function, and then answer questions about the amplitude. So first, as always, let's make sense of the question. So we have a toy tractor wheel. So obviously I found this cool tractor picture online. So what we know? We know that the radius of the wheel is 1.5 meters. So that's the radius of the wheel, and I just happened to draw it there. I could draw it in other places as well. Next, we know it rotates clockwise. So clockwise, like the minutes of a clock, go in this direction around in a circle. And then we're told that there's a stone in the rightmost point of the wheel. So furthest to the right would be a point right about here. So that red dot represents the point. So we want to be able to sketch a sine graph for the height of the stone above the ground as the wheel rotates. So let's think about what's going to happen. So the height of the wheel as it rotates. So right now, what's the height of the wheel above the ground? Well, we know that the wheel has a radius of 1.5, and I drew my radius line here, but I could also draw my radius line like this. Oh, so right now, the moment we start, that stone is 1.5 meters above the ground. And then it's going to rotate in this direction. Again, that's clockwise. It's going to rotate down, and then up again, and then up to the top, and then back here, and keep going around. So I created a slightly nicer picture here of just the wheel, so we're not distracted by that pretty truck. And there is the rightmost wheel. So again, as it rotates, so let me just rotate. So really, we're only focused on where that stone is, the yellow dot, and we can see that it goes, well, it goes around and around, but what we really want to focus on is the height. So again, if it starts here, we know that that's 1.5 meters above the ground. And then it'll rotate here. Well, what would the height be here? Well, it's on the ground, so the height is considered to be 0 meters. And then it'll rotate here back to 1.5 meters, and then rotate to the very top of the wheel, which would be how much above the ground? And then back here. So let's get some numbers down. So these lines here will represent the absolute minimum and absolute maximum of the wheel, and obviously also the middle point of the wheel. So now as I rotate it, we can see that it sticks always between them. So again, as we discussed, we know that it is 1.5 meters above the ground to begin with, and that's because the radius of the wheel is 1.5 meters, which I could draw there, or I could draw going straight down, so that's 1.5 meters, so the stone is 1.5 meters above the ground. Now as we start to rotate the wheel, beep, 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 it's going to now be on the ground, also known as 0 meters above the ground. Then I'm going to rotate again, and it's back to 1.5 meters, and then rotate up, and now it's 1.5 meters up. So again, here's the tractor tire, 1.5 meter radius, so this is also 1.5 meters, so that's 3 meters. And then as it keeps rotating, it's basically going to just move between 1.5 meters, 0 meters, back to 1.5 meters, 3 meters, and so on. So let's think about this a little more carefully now. So I'm going to try to start sketching my little diagram. So the middle line is at 1.5 meters, 0 meters will be the minimum, and 3 meters will be the maximum. So let me just remove these because they're sort of distracting. So we know that the stone starts at 1.5 meters above the ground. And then as I rotate it clockwise, it then ends up, after rotating 90 degrees, so after going 90 degrees, it ends up at the ground. Then I'm going to rotate it again, another 90 degrees, and it's back to 1.5 meters. So it's back here, and another 90 degrees, so that's at 180 degrees. And if I rotate it again, another 90 degrees, now I'm at 270 degrees total rotation, and you can see that the point is now at its maximum, 270 degrees, and then with one more 90-degree rotation, I've done a full circle, and I'm back to the starting level at 1.5 meters. So back here, 360, and you should recognize that this is a lovely and beautiful sine curve, because as it rotates, it's rotating through a circle, and anything that rotates through a circle will be sinusoidal in nature. It starts at 1.5 meters, and then it's rotating down to the minimum, and then it's going to rotate up through that midpoint to the maximum, and then rotate back down to the middle, and then it's going to repeat and repeat and repeat as long as that tractor tire is spinning. So let's now make a nicer looking graph. So I don't know if I'm going to make this graph the same way your teacher might, but I like to draw usually with light pencil, but in this case, a computer line that I will shade in a different color. I like to indicate where the middle line of my graph is. So that middle line, that 1.5 line, I like to be able to see that pretty clearly. It certainly helps me draw a slightly better graph. So I'll just make it a dotted line. I also like to draw where my maximum is. This is the stuff that helps me make a pretty picture. So remember, my maximum is 3 meters above the ground, because that is the highest point, because it's twice the radius of the circle. So again, I'll sort of make it a slightly smaller looking line. And then the minimum as well, I sort of guiding me to draw better pictures. I'm not much of an artist at all, but I mean, using a computer is easier, but by hand, this really helps my brain figure out how to draw something nicely. So we'll do this as well. Okay, so those 3 lines are sort of my guiding lines, and they represent, again, the minimum, the middle point, and the maximum in terms of the height above the ground, which are 0, 1.5 meters, and 3 meters. Now, what we know is that the tire starts, so what color should I use? Hopefully blue will show up. We know that the stone in the tire at 0 rotation is right in the middle of the tire, and then it rotated down. And it took 90 degrees, which is a quarter turn, to get to the bottom or the ground level. Then it rotates back up, and by 180 degrees, it's gone halfway around the circle. So it's back up to 1.5 meters. And then it's going to continue to go up, and then it's going to come back down to 360. So again, those are the same points as when I made this graph, but I'm now trying to make it a little nicer on an actual piece of grid paper that was given. And then I just have to connect the points into a reasonably smooth, ooh, it's hard with this stylus. And I don't know if your teacher wants you to do this, but I always sort of do this because they gave me more graph, so I'll just do that. So that's what it looks like. Now, I should probably label a few things. Like, for example, this is the graph of height of stone at degree of rotation. So it's not height versus time. I'll know we do a lot of graphs like that. This is height of stone at a degree. So at 90 degrees of rotation, it's on the ground, and so on. So I'll label this axis as theta, and this axis is h, where height is measured in meters. So that's my graph. Not much else I can add to it, I don't think. Well, there you go. Pretty nice looking graph. And now we have to write an equation that represents this function. So what I've got here is I've got a picture that represents a normal untransformed sine curve. We can see there's a maximum at 1, a minimum at -1, a middle line at 0, and then it rotates one full cycle between 0 and 360. And here's a really nice computer-made image of the tractor tire that we just looked at. And you can see I've sort of emphasized that middle line. So we need to compare the normal sine curve to this curve to see how to transform it. So I always like to start with the easy stuff, which is let's look at if I have moved the middle line up or down. So the middle line of a normal sine curve is at 0, and here the middle line is at 1.5. So that means that I know that at the very end of the function I'm going to write eventually, I'm going to add 1.5. So that's like the d value in a transformation statement. It just moves the graph up or down. That middle line is all you need to tell you if it's been moved up or down. It's supposed to be at 0. This one's at 1.5. I guess it moved up. Now I'm going to look at the amplitude. So the normal amplitude is the distance between that middle line and the maximum, and also the distance between the middle line and the minimum. Those have to be the same value. So we know that it's 1 unit in the normal sine curve, so it's 1 up and 1 down, so normally the amplitude is 1. On this graph, I have to go 1.5 meters up or down. So that means the amplitude is 1.5. And amplitude represents the A value in the transformation. So now I know that at the front of the graph, I have to have 1.5. But if you'll notice, this graph also goes down and then up instead of up and then down, which means it's been flipped upside down, which is a negative in front of the amplitude. Now, nothing else is different because this took 360 degrees for one full rotation, and it starts where the normal sine curve starts, which is a starting point is at 0. It goes up, mine goes down. I already dealt with that with the negative sign, and that means we don't have to worry about any other transformations. So we didn't change any of the interior things, the horizontal changes, but we did have an amplitude change, both by making it negative and stretching it to 1.5 meters up and 1.5 meters down. And then we also moved that middle line 1.5 meters above the 0 line. So that is the equation. It's not in function notation, so hold on. H at theta equals negative 1.5 sine theta plus 1.5. There's the equation of the height of that stone on the rotating tractor wheel. Finally, we have to talk about the amplitude and what does it represent. Well, we just talked about the amplitude, right? The amplitude is the distance between the middle line and the minimum, or the middle line and the maximum. They have to be the same. So the amplitude in this case is 1.5 meters. And what is it that that represents? So where did 1.5 come from in the original situation? So 1.5 was the radius of the tire wheel. So what does it represent? The radius of the tire. Because as the tire's spinning, that minimum and maximum, representing sort of the lower amplitude measurement and the upper amplitude measurement, that sets the confines of how this tire is going to rotate. It'll get as low as this point and as high as this point, but it's always going to be rotating sort of around those 2 points. So the amplitude, the biggest measurement and the smallest measurement, are confined by that 1.5 meter value. Okay, well, I hope that was helpful. Please continue getting help when you need it. Please continue working on math and studying math. Thanks for watching.